So, when we are dealing with multi-core systems where multiple applications can run on multiple cores, and these applications can be multi-threaded applications or multi-program applications. When applications are running on multiple cores, they share the memory, and so once we have a shared memory system associated with our multi-core systems, we need to provide the correctness of this shared memory. And the correctness of shared memory is provided by using coherence as well as the consistency. So, we already discussed the cache coherency mechanisms and protocol associated with cache coherency maintenance. And now, in this module, we are going to discuss the memory consistency. And before formally defining this memory consistency, now we are going to see a set of examples, and that will motivate us to go for memory consistency models. So, consider a two core system where in core 1 we are executing this piece of code where there is a store instruction which is storing a value new into variable data, and another store instruction which is going to set the flag bit. And in core 2 we are executing this piece of code where we are actually loading the value of this flag into a register R1, and then there is a branch instruction which is actually checking whether R1 is not equal to set or not. And based on this condition outcome, we either go back to this L1 executing this load instruction once again, or otherwise we are going to execute second load instruction, that is R2 equal to data. So, given this piece of code, now what are the possible outcomes we can expect? So, as a programmer, when we write this piece of code, our expectations will be if the load 2 is executed, that indicates that this branch condition is false. So, the branch condition false indicates that R1 is equal to set. When R1 is equal to set indicates that the flag is equal to set. So, as a result, when flag is equal to set here, then automatically this first store instruction should have been completed. So, that means the data should get a value new. So, in that scenario, now R2 should get a value new. Now, we will see what are the possible outcomes we will get. So, if the output is set and new for R1 and R2, then this is according to our expectations, or this is according to programmer's expectations. But some scenarios, what is going to happen is we can get a value set comma 0, where R1 is going to have value set and R2 is going to have a value 0. But this is actually against the programmer's intuition. When a programmer writes this piece of code, he assumes that the store 1 is going to execute first, then store 2, and once store 2 is executed, so flag is equal to set. So, as a result, this branch condition will be false, and then it will execute this second load instruction, and this second load instruction is going to get the value new. But so we are actually getting set comma 0. So, that is nothing but, so this second store instruction is completed before the first store instruction, and because this store is completed, so the condition is false. So, as a result, we can execute this load instruction, and when we are executing this load instruction before this store instruction, so we are going to get the value of 0 in R2 register, because initially data is equal to 0. So, this is against to the programmer's intuition. Now, again we will see another example. Here again we have two cores, core 1 and core 2, and core 1 is executing a store instruction followed by a load instruction. Here we are storing the value new, and in the load instruction we are reading the value from memory location y. Similarly, core 2 is executing a store instruction followed by a load instruction, but here store 2 is actually storing a value new into memory location y, and the load instruction is going to read a value from memory location x to register R2. So, now what will be the possible outcomes from this piece of code? And initially our x and y values are 0. So, now as a programmer our expectation will be, so it can execute in this order, either S1, L1, S2, L2, or S1, S2, L1, L2, or S1, S2, L2, L1, or S2, L2, S1, L1. So we can have multiple combinations here, and but our expected values will be either R1 R2 will have 0 new, or we can have value new 0, or we can have a value new new. So this 0 new will get in a scenario where we execute this R1 is equal to 0. So that means, so we have to execute this S1 L1 first before S2, and after that we can execute L2. So effectively we can get this outcome when we execute the instructions in the order S1 followed by L1 followed by S2 followed by L2. Similarly, if we execute the instructions in the order S2 followed by L2 followed by S1 followed by L1, then we are going to get the value new comma 0, because we are executing S2 first. So we are storing new into memory location Y, and after that there is an load instruction which is actually loading the value from memory location Y to the register R1. So as a result, register R1 is now having the value new. And also in the previous sequence, because we are executing load 2 before store 1, so as a result we are going to read the old value from memory location X. So as a result, R2 is going to have the value 0. This is also a valid sequence according to the programmer's expectations. And now we will see the third outcome, which is new and new. So this can happen when we execute the instructions in this order S1, S2, and after that L1, L2, or otherwise S2, S1, after that L1, L2 or L2, L1. So we perform the store operations first, and then we perform the load operations, then we can get this value new and new. So as a result, so when we write this piece of code as a programmer, our expectations will be we either get 0 new, new 0, or new new. But this piece of code can also give an unexpected outcome which is 0 0. So that is, so the load instructions may be executed before the store instructions, and if you do so, then automatically you are going to get the R1 equal to 0 and R2 equal to 0, and after that you are actually writing to the memory locations X and Y. So because our underlying hardware may execute instructions in a different way than what the programmer is expected. As a programmer, when we write this code, we expect that our first instruction is going to execute first, then the second instruction and third instruction and so on. But our hardware and as well as the compiler can rearrange our instructions in the program to maximize the performance. We already discussed as part of superscalar processor design, instructions can be reordered as long as they are not having any true dependence. So once we are executing the instructions in an out of order fashion at the hardware level, so the programmer has no clue how the instructions are executed, and as a result we will get some unexpected outcomes than the set of expected outcomes. So as a result, the entire correctness of the system will be at stake. So as a result, we need to have a memory consistency models which will give us, as a programmer, it will give us some set of the rules saying that you can expect these possible outcomes, and also at the same time it is going to provide the set of rules to the hardware designers or the compilers saying that you cannot go beyond this particular limit for rearranging the instructions or applying any of the optimizations. In other words, so memory consistency model typically gives specifications of the allowed behavior of multi-threaded programs executed on shared memory. So it provides the information to both the programmers as well as the system designers. For the programmers, it will give set of indications so that the programmer can use these indications to reason about the possible results and the correctness of the program when it is executed. Similarly, the system designer can use these indications to constrain how much accesses can be reordered by the compiler or the hardware so that we can achieve maximum performance improvement without losing the correctness issues. But anyway, we have in our systems the coherence support. When we have the cache coherence support, do we really require memory consistency on top of that? Yes, indeed, we require consistency even when we have the coherence support in our system. So, the goal of cache coherency is to make the caches in multi-core systems invisible, because generally when we write a program, for the programmer, he does not care whether there are 2 levels of caches, 3 levels of caches, private cache, shared cache and so on. So, his idea is there is a processor and the memory, and he writes the programs thinking that the entire code and the data will be there in the memory, and whenever the program requires, then the data will be supplied to the processor from the memory. And but once we have this private caches and the shared caches or the multi levels of cache hierarchy to improve the overall performance, then we will have a cache coherency support, so that the cache coherency ensures that the data, the replicated data that is available with multiple private caches is in consistent state or in coherent state. So, as a result, this cache coherence setup ensures that the caches in the multi-core system are invisible, but at the same time it provides the correctness from the coherence point of view. And also we know that the cache coherence deals with only one block at a time, and it is silent with the interaction of accesses of multiple cache blocks. When there is a store instruction from one processor, then if any other processor is going to read from the same memory location, then the cache coherency ensures that they are going to get the correct data, either by using an invalidation based protocol or the update based protocol. But if processor P1 and processor P2 both are performing a store and load operations on different cache blocks or to different memory locations, then cache coherency is not going to communicate this write to the processor which is going to read, because effectively this write is to a different memory location and read is from a different memory location. So, in other words, cache coherency always deals with whatever the operations we are performing for a single memory block, not for multiple memory blocks or multiple cache blocks. But whereas in the case of memory consistency, we actually deal with the operations that are performed on the memory, irrespective of whether it is for a single memory block or for a multiple memory blocks. And also another thing is, we can design our multi-core system without caches. We can have multiple cores and then the memory. So, there is no cache. Once there is no cache, there is no need of cache coherency protocols or cache coherency design. But even then we need the support of memory consistency. So, this actually says that memory consistency is required irrespective of whether we have a support of cache coherency or not in our systems. But because all the current multi-core systems have multiple levels of caches with the private caches and the shared caches, so as a result we have support of cache coherency. So, we can use this cache coherency mechanism for helping our memory consistency models. So, we can use this cache coherency as a block box that implements a single write and multiple reader invariants. When I say single write and multiple reader invariant, so when we have a cache coherency system in our multi-core processor, then when we perform multiple reads, we are not going to change the content of that cache block or the memory block. But whereas when we want to perform multiple writes, at any point of time only one write will be applicable on a memory location or a cache block, and so as a result all the writes to the same block will be serialized, and so as a result, so the block content will be changed with respect to the latest write. So, in other words, so when we implement a cache coherency system, so automatically when we perform one write, so we will get the corresponding data updation in our the memory block or the cache block, and when we perform simultaneously multiple reads, we are not going to change the state or the contents of the block. So, that is what the cache contents will not be changed when we perform multiple read operations, but the cache contents will be changed with respect to a single write at any point of time. And also when we have multiple writes we want to perform on a cache block in a multi-core system with a cache coherency support, the cache coherency system ensures that the writes will be serialized. At any time only one write will be happen to that particular cache block, and it will update the contents of the cache block. So, in summary, we are going to use this cache coherency as a tool to aid our memory consistency models, whatever we are going to design. So, in this module we are going to discuss the sequential consistency model, and in the next module we are going to discuss total store order model as well as the relaxed consistency model. Lamport has defined the sequential consistency as follows. A multi-core system is sequentially consistent if the result of any execution is same as if the operations of all the processors were executed in some sequential order and the operations of each individual processor appear in this sequence in the order specified by its program. So, it says that when we have a multi-core system where multiple applications are executed on each of these cores, and each of this program is going to execute instructions in the program order, and also because we have multiple programs executed simultaneously on this multi-core system, we can interleave the instruction execution from all these applications in any order. And so, as long as it produces a value which is consistent with any of the interleaving orders of these instruction executions, then we can say that the entire system is said to be sequentially consistent. So, we now explain the sequential consistency concept with an example. So, consider a 2-core system where core 1 is executing a program that consists of a store instruction and a load instruction, and core 2 is executing another program which is having again another store instruction followed by a load instruction. So, now once we have these two programs running simultaneously on these 2 cores, now we will see how what will be the expected outcome and whether the expected outcome is inconsistent with the sequential consistency definition. So, here the core 1 can execute its 2 instructions first, that is a store 1 and load 1, and after that core 2 can execute its instruction, that is store 2 and load 2. So, if we consider this order, so store 1 load 1 is coming first and store 2 load 2 is coming next, and here we can clearly see within a program the instructions are in the program order, because our first program is having store 1 first followed by load 1. Similarly, the second program is having store 2 first followed by load 2. So, in both the programs we are not violating the program order. So, this is according to the sequential consistency definition by Lamport, and also so we are executing instructions in some interleaved fashion. Here in this particular example we are executing the instructions of program 1 first followed by the instruction from program 2. So, as a result we are getting an outcome 0 and new, and this is consistent with the Lamport's sequential consistency definition. So, as a result we can consider this as a valid outcome for this piece of code. Now, consider another way of executing these instructions. So, here we are actually executing the instructions of second program first, then we are executing the instructions from the first program. So, here so we are executing the store 2 followed by load 2, which is in the program order as specified by second program. Then we are executing store 1 followed by load 1, which is again in the program order as specified by the first program, and again this is also so one of the interleavings of the executions, and this is again consistent with the sequential consistency definition. So, as a result whatever the outcome we are getting here is also valid. So, effectively the outcome new comma 0 is also a valid outcome. So, these two are according to the programmer's expectation. Now, consider other alternative. So, here we are executing store 1 first, and then we are executing one instruction from the second program, that is store 2, and then we will come back to program 1 on core 1 and we execute the next instruction, that is load 1, and finally we go to core 2 and execute the leftover instruction from program, that is L2. So, as a result this is also not violating the program orders in individual programs, and this is also another interleaving of instruction execution. So, the outcome of new is also valid according to the sequential consistency definition. So, once we have a system supporting sequential consistency, then programmer can expect either 0 new 0 or new as outcomes for this multi-threaded program execution. But so here we may get an outcome of 0 also, as long as our hardware is not respecting the memory consistency model definition or the specifications, then it can rearrange its instructions. As a result, we can get some outcome which is not consistent with our sequential consistency definition. So, see here in this particular piece of code, we are executing first the load 2 instruction, and then we are going to the program 1 that is executed on core 1 and execute the store 1 and then load 1, this is in the program order, and finally we are executing store 2 from program 2. We can clearly see here we are executing load 2 first before the store 2, and which is actually violating the program order. But according to the sequential consistency definition, each of the individual programs running on our multi-core system should respect the program order. But here, because this load 2 and store 2, these are independent, and if our underlying hardware is looking at this independent instructions and then rearrange the instructions to execute for performance improvement, then it can execute load 2 first before the store 2, and as a result we will get a completely unexpected outcome here. And as a result, this particular outcome is not consistent with respect to the sequential consistency definition. So, now if we have this memory consistency model defined in our multi-core system, and once this is defined, then automatically underlying hardware also has to respect this memory consistency model, and accordingly it has to look at when it is rearranging the instructions for performance optimizations. Even when there is set of independent instructions that can be executed in out of order fashion, if it is going to violate our underlying the memory model or memory consistency model, then the hardware should not go for this rearranging of the instructions, because we are not worried too much about the performance, but we are worried too much about the correctness. As long as the correctness is maintained, then we can go for any rearrangement of instructions to extract more performance improvement. But if we get significant performance improvement but without respecting the correctness, then that is of no use. So, as a result, we have to give more importance for the correctness, then we can think of going for the performance improvement techniques. So, after discussing that example, now we will formally define our sequential consistency. So, an execution that is said to be sequentially consistent requires that all the cores insert their loads and stores into the global order respecting their program order. Here this less than p indicates the program order, and less than m is indicating the global memory order. So, here when we have multiple applications running on multiple cores of our multi-core system, and each of the core is actually issuing their load and store instructions from the corresponding application in the program order, then we can construct a global memory order like this. So, if there is a load instruction from a memory location A and there is a load instruction from memory location B, and these two are from the same application and they are following in the program order, then in the global order also we can just have this order. So, effectively this particular statement says that if a load from a memory location A is coming before load from a memory location B from a particular program, then in the global order also this load A will come first before load B. So, this is actually saying that we have to maintain the load to load order. So, that is what it says, because this is from a single application where we are actually sending a load instruction for a memory location A, and then we are issuing a load instruction for memory location B, and if they are in the program order, then in the global order also they will come in the same order. So, first load A will come and then load B will come. So, now consider another scenario. So, we have a load instruction from a memory location A followed by a store instruction from to a memory location B in the program order. Now, in the global order also, global memory order also, this load has to come before this store. So, that is what is given here. So, this is called as load to store ordering. So, if there is a leading load followed by a trailing store in the program order, then in the global order also the load should come first, then the store. And now the third condition says that if there is a store to a memory location A followed by a store to a memory location B in the program order, then in the global order also the store to a location A comes first before a store to a location B. That is what the store to store ordering. And finally, so if there is a store to a memory location A coming first in the program order before a load to a memory location B, then in the global order also this store should come before this load. So, that is what the store to load ordering. Effectively, when we have the sequential consistent model defined in our multi-core system, then we have to respect the order between every pair of load and store instructions. Load to load order should be maintained, load to store order should be maintained, store to store order should be maintained, and finally store to load order should be maintained. And also, every load gets its value from the latest store before it to the same address. So, what is this? For example, in our program we have a store instruction to a memory location A, and then there is a load instruction from the memory location A. That means the store and load are from the same application and to the same location. So, as a result, this subsequent load should get whatever the value produced by the previous store. So, this will be perfect because our instruction execution from a single program follows the program order. But what about if the store is from one application and the load is from some other application? So, how do we do that? So, effectively, let us say program 1 which is executed on core 1 is issuing a store instruction to a memory location A, and a program running on core 2 which is actually trying to read the value from the same memory location A. So, now if in the memory order, the global memory order, if the store is coming first, then this load from the second core should get the value supplied by the store instruction only. And also there may be multiple writes to the same location, but when we issue this load instruction, then the load instruction should get the latest return value to that particular location. So, that is what we are giving here. So, once we execute the instructions in a sequential consistent manner, then the entire implementation is said to be sequentially consistent. So, in other words, an SE implementation permits only SE executions. When we say our system is supporting sequential consistency, then all the instructions whatever they are executed on our system should be supporting sequential consistent execution only, and this sequential consistent execution will respect this load to load, load to store, store to store, store to load ordering, as well as the load is always going to get the latest write to that particular memory location from where this load is going to read. So, how do we implement this sequential consistency in our system? A naive method is, so consider a unicore processor where this unicore processor is actually supporting this multitasking. So, that means So, this unicore processor can execute one task now, and then there may be a context switch, and then it will go to another task and execute, and then again go to third task and execute for some time, and then there is a context switch and come back to the first task and execute effectively. So, we have a single core and multiple tasks, and at any point of time this core will execute instructions from only one of the tasks, and when we are executing instructions from one particular task, we know that we are executing the instructions in the program order in that particular task. So, effectively this is like a switch model. Also, we can extend this for a multi-core system or a multiprocessor system, where we have multiple processors or multiple cores, and all these cores are connected to the memory. And now, when an application running on any of these cores, when it is issuing the requests, then if these requests are load or store requests, then they have to go to the memory, and now this memory is going to be accepting the requests at any point of time only from one particular core, and once it processes that particular instruction, then it can move on to another core and then accept any load and store instruction from the corresponding application running on that particular core, and so on. So, in other words, this is acting like a memory switch, and there may be requests from all these cores, and at any point of time this switch is going to take or accept the request from one particular core at any point of time, and after processing that, then it will move on to the next one randomly, and then again it will take the request from that particular connected core and then process, and then again switch to some other core and process the request, and so on. So, this way we can simply implement our sequential consistency in our multi-core memory system. But most of our current systems, or almost all the current multi-core systems or multiprocessor systems, actually have the cache coherent memory system, where we will have a set of private caches for each of the cores, and then there is a shared cache or the memory, and we will have cache coherence support, so that the entire memory hierarchy will maintain the cache coherency. And once we have this, we can treat this as a block box, and all these cores are connected to this block box, and at any point of time when these multiple cores are sending their requests, only one request from a particular core can be accepted, and it will be processed by this cache coherent memory system, and the response will be supplied. And after that, again this system is going to accept a request from some other core, and so on. So, for example, consider a bus based simple multi-core system, where we have 4 cores connected to a common bus, and each of these cores, when they want to get some data from the main memory or the shared cache, then they place their request on the bus. But note that multiple cores cannot place their request simultaneously on the common bus. So, for that they have to go for bus arbitration logic, and they will request for the bus, and the bus will be given for only one of the requesting cores, and whoever wins the arbitration, they are going to place their transaction on the bus, so that the memory or the shared cache is going to supply the data for that particular request, and after that the bus will be released, and again all other cores again compete for the bus, and whoever wins, then they will send their request on the bus, and so on. So, that way we can implement our sequential consistency efficiently in this. At the same time, we are having the cache support to improve the overall performance. But this particular cache coherent memory system can also be viewed like the set of private caches associated with each of the cores, and then the remaining component of the cache coherent memory system. It consists of maybe a shared cache followed by the main memory, and so on. So, once we have this type of design, what is going to happen is, as long as applications are getting hits for their load and store requests in their local caches, then they do not have to deal with the common bus to send their transactions to the shared cache or the memory. So, that way what we are going to do is, once we have this cache coherent system with the private caches, then rather than restricting only one core sending the request to the cache coherent system, now multiple cores can send their request to their private caches. But if any of these cores miss in their private caches, then again they have to go for bus arbitration logic to get the exclusive permission to use the bus which is connected to the shared cache or the memory, so that they can send their request on the bus, so that they will get the response from the shared cache or the memory. So, at least as long as we have our private caches which supply the data for the request from this course, then we can improve the overall performance, and this also ensures that the parallel execution from multiple cores, and that will improve the overall performance. So, effectively, once we have a cache coherent system with private caches and the shared caches, we can implement the sequential consistency efficiently, and at the same time we can ensure the performance improvement by parallelizing the request processing from multiple cores by using the private caches associated with the corresponding cores. But the sequential consistency puts a restriction that we have to respect the ordering between loads and stores. If there is a load and a store, even when these load and stores are to different memory locations, we have to respect that order in our global memory order, and as a result the sequential consistency is going to degrade the performance. So, now we will see what are the sufficient conditions for preserving sequential consistency. So, consider a piece of code. Here we consider 3 cores in our system, where core 1 we are executing a store instruction, that is a equal to 1, and core 2 we are executing a branch instruction, that is a while a equal to 0 condition, and then there is a store instruction b equal to 1. And then in core 3 we are executing this while condition, and then we are printing the value of a. So, now when we write this as a programmer, our expectation will be, so this print statement should print the value of 1, because it is printing a, and this can be possible only when we come out of this while loop. We can come out of this while loop only when b is not equal to 0, but b is not equal to 0 only when we perform this store operation. But when we perform this store operation, that indicates that we already executed this while loop, and we exited from this while loop, but we exit from this while loop only when we have a equal to 1. So, that is what we have given here. So, effectively as a programmer, our expectation will be, so as long as this instruction is not executed, so we will be in this while loop continuously, and whenever we execute this instruction, this store instruction, then this condition will be false, so that we will go for subsequent instruction to this while, and which is another store instruction, that is b equal to 1. And when we perform this, then automatically this core will exit this while loop, and it is going to print the value a, and a will be 1. Because we know that in this particular scenario, if b is equal to 1 happens, then automatically a equal to 1 should have been completed already. That is what the programmer's expectation. But in our system, we may not have printed a equal to 1. We might have printed a equal to 0 if our system is not supporting the sequential consistency. When the processor 1 is going to write to a variable a, it is going to send an invalidation signal to all the processors, because we are assuming that here our system is having the cache coherency support. When we have a cache coherency support, and whenever any processor is going to write to a particular location, the first thing it is going to do is it is going to send an invalidation signal. And also here we are assuming the invalidation based cache coherency protocol is designed in our system. Also assume that the local caches in each of these processors have initially some value a equal to 0. And now when we perform this store operation, we sent an invalidation signal, but unfortunately this invalidation signal is reached only to processor 2, but not to processor 3 or core 3. So, whenever invalidation signal is reached at core 2, this core 2 is now going to perform this the load operation, because a equal to 0 is effectively it has to load the value, and it finds that this variable is or the block which is holding this variable a is invalidated. So, as a result it will go to the the corresponding memory, or it goes to the cache associated with this core 1 and it gets the value a equal to 1. And once a equal to 1 is read, then automatically this while condition is false in core 2, and then it immediately executes the b equal to 1. When core 2 is going to write a value 1 to the variable b, it is going to send an invalidation signal and assume that this invalidation signal is immediately reached core 3. But the previous invalidation signal, whatever is sent by core 1, is not yet reached core 3. That may be because the path connecting between core 1 and core 3 is highly congested and the request is stalled somewhere. So next time when core 3 is executing this while loop, effectively it has to load the value of b, because previously b is invalidated. So effectively now it goes to cache associated with core 2 to get the latest value of this b, and it is going to get the value as 1 for variable b. So this while loop is exited, and then immediately it is going to execute its printf statement, because when it is going to print the value a, because its local cache of this core 3 is still having the old value. The reason is whatever the invalidation signal sent by core 1 is not yet reached core 3. So as a result, it is not invalidated its previous a value. So when we are going to print the value of a, then it is going to print value as 0, and that is actually inconsistent. And so as a result, when we want to implement sequential consistency in our model, in addition to respecting the program order, in addition to respecting the global memory order, we also need to have set of conditions. These are sufficient conditions to ensure the sequential consistency. Every process issues a memory operation in the program order. So that is, we already mentioned in the formal definition of sequential consistency, and we have to consider write completion. So write completion says that after a store is issued, the issuing process waits for the store to be complete before issuing any other operation in the program order from that particular application. So consider a simple example. Let us say core 1 is now issuing a store instruction, and after this a equal to 1, there may be another instruction, but this core 1 cannot execute this subsequent instruction unless this store is said to be completed. When I say store is said to be completed, it has to send an invalidation signal. If we are considering an invalidation based protocol, it has to get the acknowledgement from all the cores, then only it can write the value to the corresponding variable, or in other words, we can perform the store operation, and then only we can proceed with the subsequent instructions in the program order. So first one says all the instructions should be executed in the program order, but the second one says when there is a store instruction, we cannot proceed with the subsequent instruction unless the store is said to be completed. And the third condition says that the write atomicity. So here, after a load is issued by a process, the issuing process waits for this load to complete, as well as it has to wait for the store which is actually supplying the value to this particular load. So it has to wait for the store to complete. In other words, let us say here we consider, so processor P2 issuing a load instruction, that is a equal to 0. When this load is issued, this process which is running on processor P2 cannot start executing the subsequent instruction unless this load is completed, as well as any store which is actually supplying the value to this particular store. So here we can clearly see this load is actually loading value from memory location A. Similarly, this process which is running on processor P1 is actually performing a store operation to the memory location A. So now we cannot start executing this b equal to 1 unless this load operation is completed, as well as this store operation is completed. If we ensure that, then this piece of code is going to print a value a equal to 1 in core 3, because when we are executing this printf statement, So, that indicates that we exited from this while loop, and when we exited from the while loop, so we have b equal to 1, but when b is equal to 1 is performed, that indicates that the previous operation is already completed. But the previous operation consists of a load, and this load is said to be completed only when any store which is actually supplying the value to this load is also said to be completed. So, that means this a equal to 1 is said to be completed. When a equal to 1 is completed, then this printf statement is going to print a value 1. So, that is what this write atomicity. So, these are the sufficient conditions to ensure the sequential consistency. In summary, when we want to maintain sequential consistency, we have to go for this set of conditions. These are write atomicity, which ensures that you cannot proceed with any instruction subsequent to a load instruction unless the load is completed, as well as any store which is supplying the value to this load is also said to be completed. And we also have to maintain the write completion, where when we issue a store instruction, we cannot proceed with subsequent instruction unless this store is said to be completed. And also we have to issue the instructions in the program order, and this program order condition will be for each of the programs. So, now we will see whether our 3-state write back invalidation protocol, whatever we discussed as part of cache coherency protocol, will provide the sequential consistency or not. So, for sequential consistency, we have to ensure that our sufficient conditions are met. The first one is issuing the instructions in the program order. So, here we assume that all our programs are issuing the instructions in the program order. So, we do not have to worry about the first condition. But the second condition is the write completion, and the third condition is write atomicity. Now, we will see the write completion. So, write completion is detected whenever a write miss or an invalidation transaction is placed on the bus and the write is performed in the cache. According to our 3-state the write back invalidation protocol, whenever we are going to perform any write operation, if it is going to get a hit in the local cache, then it is going to place an invalidation signal on the bus. For example, see here, you may have a block in the shared state and you are going to perform a write operation, and if the write is a hit, then we are going to change the state from shared to exclusive here, and we are going to place a transaction, that is invalidation transaction, on the bus, so that any other caches which have the data in the shared state for this particular block, they are going to invalidate by using this state transition. So, shared to invalid. So, as a result, once we place this invalidation signal, everyone in the bus based multi-core system will invalidate their copies, so that the requesting core which is going to perform this write operation will actually perform the write operation on the corresponding block. Similarly, so if you have a block in the exclusive state, and if there is a write request, because exclusive state indicates that only one particular cache has that particular block in the modified state. So, if there is a write operation, then you do not have to place any transaction on the bus, and because you do not have to communicate this information to all other the caches, because they do not have the data. So, as a result, you can peacefully perform your write operation there without changing the state. In this particular case, you do not have to place any the transaction on the bus, and also because you have the data in the modified state, you can perform multiple writes to the modified block, and so as a result it is not going to create any problem. So, in this case also we can say this write is said to be completed. Whenever you have a block in dirty state or a modified state and you are performing a write operation, you do not have to explicitly communicate with all other caches, and you can perform your write, and this write is said to be completed locally, but this is not going to create any incorrectness according to the memory consistency. And now consider another scenario. For example, you want to perform a write operation to a particular block and you incur a miss. Whenever there is a write miss, then for this, for example, CPU write miss, then we are going to place a write miss transaction on the bus, whether the block is in the shared state or an exclusive state. For example, here also if there is a write miss, then we are going to place a write miss transaction. So, that means whenever there is a write miss, we are going to place a write miss transaction, and all the cache controllers will snoop on the bus and they respond to this write miss transaction and invalidate if they have the copy in their local caches. So, after they invalidate, then the requesting core can perform the write operation. Then we can say this write is said to be completed. So, whether it is a write hit or a write miss, so using this write miss transaction or invalidation transaction on the bus, we are performing this write completion successfully. So, this is satisfying the second sufficient condition for our sequential consistency. Now, we will see the write atomicity. So, write atomicity says that when we issue a load instruction, we cannot proceed with any subsequent instruction to this load instruction unless this load is said to be completed, and also if any other store which is producing the value for this load, that also needs to be completed. So, this write atomicity is actually provided by using this read completion. So, when we have a read completion, then according to the state transition diagram, this read completion is met because a read is either causing a bus transaction that follows that of a write whose value is being returned. For example, there is a write operation from core 1 and it sends either the write miss transaction or invalidation transaction on the bus, so that if core 2 has that particular block of data, it invalidates. And after that, let us say core 2 is issuing a load instruction. So, now core 2's load instruction sees that the block is invalid and then it has to request for that particular block. So, then core 2 is going to place a transaction, that is a read miss transaction on the bus. So, that is what is specified here. So, if there is a request, a read request from core 2, this core 2 can send a bus transaction, and this bus transaction actually follows a write operation or a transaction corresponding to a write request from core 1. So, that is what is given, because this core 2 is going to get the value supplied by a store instruction produced by our core 1. So, that is what is. So, effectively when this read operation is initiating a bus transaction, this bus transaction will follow that of a write instruction which is producing the value that is required by this load instruction. Or other scenario, this read instruction is actually following another read instruction by the same processor in the program order. Consider another scenario where core 2 is actually requesting the block of data, and this block of data is either available in its cache or this block is invalidated by a store from core 1. In that case, according to this first condition, the load request from core 2 is going to get the data, and after this, if core 2 is generating another load request for the same block. So, now the second load is actually following the first load in the program order. So, that is what is mentioned here. So, this read operation can follow a similar read operation from the same processor in the program order, and the previous read operation can be a hit in the local cache or a miss in the local cache. In both the cases, it is going to get the appropriate data supplied from a previous store operation, or it is supplied from the shared cache. Or the third scenario is this read operation can follow the program order on the same processor that performs a write. For example, consider a different scenario altogether where core 2 is actually generated a write request first, and then there is a read request for the same memory location. So, now when we come to the load request for the same memory location, so this load request is actually following the previous store request from the same processor in the program order. So, that also ensures that our read is actually getting the correct data and it is said to be completed. So, effectively we ensure that write atomicity from across the processors or from the same processor. So, that ensures that our read is said to be completed by using this 3-state cache coherence protocol, and also we can ensure write completion by using these corresponding transactions placed on the bus, and that also satisfies our 3 conditions whatever we require to ensure the sequential consistency. So, with that I am concluding this sequential consistency the discussion, and in the next module I am going to discuss the total store order memory model as well as relaxed consistency model. Thank you.